Hello teachers, welcome back to section 7-2 where we were doing operations with decimals. In part 1 of the video we talked about addition of decimals, multiplication of decimals, and scientific notation. Now we want to talk about dividing decimals and also estimation and mental math steps. So to divide 128 6/10 by 4. All right, now I want you to see this problem. Usually we do it by hand, and then I show the typed up version just so you can see different ways of handling these problems. But this was really unusual, this method for solving this problem. And we haven't divided yet, right? We haven't learned any division skills as far as decimals go. So the only method we could really use, unless we went to base 10 blocks, is change this to a fraction. And we know how to divide fractions. Here's the part that wasn't very obvious to me right off the bat, and it may not be obvious to you. This number is 128 6/10, right? If I write that as a fraction, y'all, I'm going to do it at the bottom of the screen down here. So 128 6/10. Okay? You could also write that as 1,286 tenths if you changed it to an improper fraction. But look what they used. You see what they did? They multiplied the numerator and the denominator by 10. They didn't tell us. They just threw that up there as the results. And then divided by 4. I know you see that. You write 4 as a fraction. A rational number is 4 over 1. Now, how do you divide fractions? You know the rule. Keep, change, flip, right? We're going to flip this fraction. Okay? But check the next thing out. Okay, so when I flip it, again in pink, let's write in the bottom right of the screen. So 12,860 over 100. I'm going to flip that 4 over 1 and change division to multiplication 1/4. That's what I would normally do. But check this out. They reversed the 4 and the 100, and they put the 100 under the 12,860 and the 4 under the 1. Now, are we allowed to do that? Don't worry about the motivation yet. Well, why would you even want to do that? But are we allowed to do that? And you would say, yes, we are allowed to do that by the commutative property of multiplication, right? You can multiply in any order that you like. Now for the motivation. Why did they do those two things? Why did they put it over 100 or multiply top and bottom by 10? And then why did they reverse the 104 and make it 4 times 100? Well, it's so that we could easily divide 12,860 by 4. Now, remember, it would have been 1,286 when I had it before. But that doesn't divide by 4 and give you a whole number, okay? Because 4 doesn't divide into 86. Remember the divisibility test for 4 has to divide into the last 2 digits, but it does divide into 60 when we multiplied it by 10, and that gives us 3,215. And then you have this 1 over 100 here, so that makes it 3,215 hundredths, which is 32 1500ths. Now, they just did some really cute numerical manipulation to make this calculation somewhat easy to do by hand. Notice that they didn't bother to show you the 4 divided into the 12,860. That would take some long division work to do, likely. You could do that in your head. I wouldn't want to touch it in my head. I would just write it down and do it. But it's still possible here. Don't feel like you're going to have to do those kind of steps to get this done. I really think they just did that to introduce you to how you could potentially divide using decimals, but with fractions. Now, how do you do it with decimals? Notice it says when the divisor is a whole number. Let's think about what that means. The divisor, that's this guy right here, right? It's a whole number. It's not a decimal or a fraction. A rational number. The division can be handled as with whole numbers. The decimal point can be placed directly over the decimal point in the dividend. So what do we need to do? Nothing. We just need to put a decimal point right there, and then you just use your standard long division algorithm. And that's all there is to it. You just keep that decimal point holding that position. And I can show you the work right there. This is stuff I know you know how to do, right? So you say 4 divides into 12 3 times. 3 times 4 is 12. Then you subtract, and then you bring down the 8. 4 divides into 8 2 times. 2 times 4 is 8. You subtract, which is 0. You bring down the 6. 4 goes into 6 1 time. 4 times 1 is 4. You subtract, that's 2. Then you bring down the 0. And then 4 goes into 20. 5 times 4 is 20. And then we actually get a remainder of 0. Okay? So if you're dividing by a whole number, not a whole lot has changed. You just put the decimal straight above. But what if we're not dividing by a whole number? What if we're dividing by a decimal? So it says when the divisor is not a whole number, as in 1N 2032, was that 100 thousandths? 10 thousandths, my bad. Divided by 32 hundredths, we can obtain a whole number divisor by expressing the quotient as a fraction and then multiplying the numerator and denominator of the fraction by 100. This corresponds to rewriting the problem in form as an equivalent problem in form B. Okay, what did we really do? We multiplied this guy right here times 100. Why would we do such a thing? To get that decimal moved over 2 places. But if you multiply the divisor by 100, y'all, you have to multiply the dividend by 100 as well. What does that do? It also moves that decimal over 2 places. So then this is the problem that we're doing. And once again, the decimal is just a placeholder up there, okay, lined straight up, and everybody just lines up from there like you're doing regular old long division. Okay? It says in elementary school text, the process is usually described as moving the decimal point 2 places to the right in both the dividend and the divisor. Now, you're not just moving it, right? Just moving a decimal point is not allowed. You're really multiplying both the divisor and the dividend by 100 in this case. Sometimes you'll multiply by 10, sometimes you'll multiply by 100. But essentially, the outcome is moving the decimal place over. But that's not truly what you're doing. Just like, remember when we multiply decimal number times the decimal number and we just count the number of places over? That's just because of how you multiply denominators together, because remember, decimals are just fractions. Now let's spend a few minutes on mental computation. What if you had to do these calculations in your head? And most of the time you don't have to do calculations in your head, but it's convenient. Not only that, when you or your students understand mental computations, it makes the hard stuff so much easier. So these are fantastic skills to have. This breaking and bridging idea is really cool. So I'm not gonna write it down. I'm just gonna show you the typed up version so you can see what's happening. So when they say breaking and bridging, you're breaking up some of your add-ins here. Okay, so what we're doing is we're going to take 1.5 plus just the 3. Okay, that's the breaking up, right? So 1.5 plus 3, it's typed up over here for you, is 4.5. Now the bridge is you still have a 0.7 going on over here and a 4.48. Okay? But that's pretty easy to do in our head. Now you got to keep up with all this in your head. That's where it can be a challenge. What should we do next? Well, now we're going to add 4.5 plus 0.7, and there's the arrows. Now that you could do in your head too, right? That's 5.2. And there's the 5.2, and then this 4.48 just is carrying over again. 5 2/10, 4 4800ths. Were you shouting at me, telling me how I was doing wrong? Yes, I know, I was doing wrong. All right, now let's take a look at 5 2/10 and 4 4800ths. What could we do now? Well, my thought, and we'll see if it matches what the book says, is what if we take our 5.2, actually, I'm cheating. It says it over here. I'm not really cheating. 5.2 and add that to 4. We can do that in our head. That's going to be 9.2, right? Okay, so that brings us down to the 9.2, and then we can add the, or 9 2/10, and then we can add the 4800ths to the 9 2/10 pretty easily, and that's 9 6800ths. So breaking and bridging, is a really neat way to handle this. You're kind of just reorganizing your add-ins to do what's convenient. Does that work every time? It kind of depends on your problem. And especially the case with the next one. Compatible numbers really need to be compatible. So if you're adding a bunch of add-ins that are not compatible numbers, in other words, they don't add up to something really nice, then this compatible numbers thing may not work for you. But in this particular problem, check it out. This works pretty well. So if I take 7.91 and I need to add that to 4.09, your 9, 1, and your 0, 9, that adds to be 1. 7 plus 4 is 11 plus 1 is 12. Hey, easy enough. Check out the other two, right? A 0.85 or 3 85/100 added to 1500ths. We know 85 and 15 adds to be 100, which is 1. So I take my 3 and add that to 0, which is 3, plus that 1 gives me 4, and 12 plus 4 is 16. Again, they have to be compatible. If they're not compatible, this trick is not going to work for you. But if you'll notice decimals add up to nice whole numbers, this works great. Just like when sometimes things add to be 10 or they add to be 100, it's very convenient. This is the same exact idea. Now, sometimes you can make compatible numbers. What do they mean by that? Well, 2700ths, that's not fancy, but 2500ths, that's pretty nice, especially if I could make this a 75. We know 25 plus 75 is 100, right? 100 hundredths carries over to the next spot. So what do? Okay, well, if we want to turn a 27 into a 25, we can break that down as 9.25 plus 0.2. That is equal to 9 and 27 hundredths, okay? The 3 and 79 hundredths, we could rewrite that as 3 and 75 hundredths plus 4 more hundredths. Now, this calculation was easier to do. You've got 9 and 25 hundredths plus 3 and 75 hundredths. Again, 100 hundredths adds to be a 1. 9 plus 3 is 12, plus that 1 is 13. And then it's pretty easy to add the cast-offs over here, right? The 2 hundredths and the 4 hundredths is the 6 hundredths. And then you have 13 added to 6 hundredths. That's just 13 and 6 hundredths. Again, it's about what's convenient. You don't always, it's not even convenient to build compatible numbers all the time. But if you see, hey, 2575, if, well, you can make it an if and cast off some stuff and then add. I'm using some great language here, don't you think? Okay. 4, check out question 4. Balancing with decimals and subtraction. So we have 4 and 63 hundredths. And they wrote that as 4 and 63 hundredths plus 3 hundredths. Why? Well, if I could just add 3 hundredths to that 1 and 97 hundredths, I'd have a nice number. I would have 2. So it's like I'm adding it here, okay, to round that up to 2, and it's not really rounding, it's to make it a 2. To fix that issue, I'm going to have to add it here also, because you're subtracting an extra 3 hundredths, so you must have to add an extra 3 hundredths to keep this thing balanced. So then it gives me 4 and 66 hundredths minus 2, which is 2 and 66 hundredths. In your head, that seems like a really reasonable thing to do. You're just trying to keep things balanced. Here's a trick coming after this one that you may have never even thought about before. With division, okay? I'm dividing by 25 hundredths. That makes me think of a quarter. Remember, we talked about that before. You're dividing by a quarter. If you take $8 and divide it by a quarter, it's 32. That's not a bad calculation just to do in your head. But another way you could handle that is you can multiply that 25 hundredths by 4, or that quarter by 4, and that makes it $1. If you multiply the divisor by 4, you have to multiply the dividend by 4 also. Isn't that neat? That's something you could do. That's a skill you could use on your own all the time. Not only can you help students do some mental calculations, but that's going to help you. So I've got that quarter. I multiply it by 4 to make it $1 or to make it 1, and then also multiply the dividend by 4. How about rounding? Are you good at rounding? A lot of students are not good at rounding, and I'm not referring to you. I'm just talking about math students just in general are not very good rounders. Now this page goes into a button on your calculator, which I have yet to find on my TI-30X. But then I thought about it and I thought, do I really need a button in my calculator to round? I don't think so. We know how to round. If you don't, we're going to get it straight right now because I need you to fix these students and their rounding. Okay? So, if you're interested, come back to look at these directions for the fixed key and rounding. Again, I don't know, value of that, I'm not real sure. Round each of the following numbers. We're going to do this by hand. Why? Because we can. We don't need a calculator to do this. So round to the nearest hundredths. First of all, we need to find the hundredths place. This is read 7 and 456 thousandths, right? And the hundredths place has a 5 in it. That's where I'm going to round. That's not what I'm looking at to round. That's where I'm going to round. What I need to look at to round is the number just to the right. You know the rules. If that number to the right is 5 or larger, then the pink number goes up. So that's going to give me 7 point, bear with me now, I know I'm saying this wrong, 46. Because again, this number that's underlined in green is 5 or larger. That means that 5 goes up to a 6. Now that's really 7 and 46 hundredths. Okay, got it typed up for you. Boom, there it is, 7 and 46 hundredths. Now, it's pause time, so it's time for you to pause the video and round each of these 5 problems and come back and we're going to compare. All right, you ready to round? So we got 7 and 456 thousandths. We're going to round to the nearest tenth this time. Look, there's a 4 in the tenths place. I'm looking at the number directly to the right. Could care less about this 6. Not even an issue in this rounding. That could be anything that's 6. What we care about is the number directly to the right is 5 or larger, which means that 4 needs to go up to a 5. So 7 and 5/10 would be the answer there. Next problem, round to the nearest unit. What's a unit? That's the ones place. I only care about what's directly to the right, which is a 4. Could care less about that 56 over there. It is a non-issue, okay? Then that 7, does it stay 7 or does it go up to an 8? And that's your only choices. It either stays what it is or it goes up to the next higher integer. And 7 is going to go up to... No, it doesn't. It stays a 7, right? Because the number to the right is below 5. So I'm going to write my answer as 7.0. You know what I see a lot of students do? They don't write the 7 at all. They don't write the numbers before that, okay? You have to write all of the numbers until where you round, and you don't write anything past that. So this is completely gone, okay? This is completely gone. The 6 is completely gone. So we'll ignore everything past the digit just to the right, and you put a 0 where you rounded. Why do you do that? So you know where this number was rounded to. Your answer can never be more accurate than where something is rounded, okay? So now I'm rounding to the nearest thousand. So what is in the thousand? Not thousandths, thousand. So there's a 7 in the thousandths place. I look directly to the right. There's a 4 next to it. So the 7 stays a 7, right? So my answer is just 7. And you're like, no, right? That 7 has to stay in the thousands place. So I put zeros past all that. Now notice I told you don't put anything when you have a decimal and you get rid of those values. But when you're talking about whole numbers, you still have to keep that in the correct place value. All right, let's keep going. 745 rounded to the nearest 10. So there's a 4 in the tens place. I look directly to the right. Now our choices are this. The 4 goes up to a 5 or it stays a 4. Well, it goes up to a 5, correct? Now, don't leave the 7 in the front off. It's still, everything to the left of where you rounded is still part of the answer. So there's still a 7. That 4 goes up to a 5. And remember, the place that you rounded has a 0 there. So that's 750. Let's do this one more time. So 74 and 56 hundredths. We're supposed to round to the nearest 10. What's in the tens place? There's a 7 right there in the tens place. I look directly to the right. Again, I'm not looking at that 5 and that 6. I'm only looking at that 4. Because that 4 is below a 5, the 7 stays a 7. It has to stay in the tens place, so that 4 turns into a 0. Do I need to write anything for the 56? I do not. 70 is the answer there. Okay, now I have all these typed up. Matter of fact, I had pages to do it one at a time, but I'm just going to click to the final answer, and notice that matches all of your work. Okay, just a few more slides. Hang with me. Okay, how about estimating decimal computations using rounding? It says rounded numbers can be useful for estimating answers to computations, and we just practiced rounding. When computations are performed with rounded numbers, the results may be significantly different from the actual answer. I caution you to not round in the middle of computations. Now you start talking about estimating, that is the point, right? If you're in the checkout line at Walmart, you start rounding. But addition and subtraction, that's not a big deal. But when you multiply and divide by rounded numbers, your error can be significant. So please, if you ever are going for accuracy, don't use rounded numbers, or don't round until you get to your final result. It says other estimation strategies such as front-end clustering and grouping to nice numbers that were investigated with whole numbers are also work with decimals. So you can go back and study that. As a matter of fact, some of your homework has some front-end stuff going on. If you struggle with that after you go back and look up how to do it, if it still doesn't make sense, let me know, and I can do some of those for you from the video. But rounding is something most students are pretty comfortable with. That front-end stuff, you might not remember how to do it. So just keep in mind, you might want to look that up before you do those homework problems. Round-off errors are typically compounded when computations are involved. That's what I warned you about on the last slide. So be very careful about rounding in the middle of computations. It says when computations are done with approximate numbers, which means estimation or rounding, the final result should not be reported using more significant digits than used with the fewest significant digits. Okay, what does that mean? All right, so let's just say we were going to multiply in 123, and then bear with me while I just make up some crazy decimal. Okay, so that's what 100 thousandths, right? So we have 123 and 45,789 hundred thousandths. We want to multiply that by 1 and 23 tenths. Okay, here's what they're saying. You have 3 significant digits right here. Okay, over here we have 1, 2, 3, 4, 5, 6, 7, 8 significant digits. Our answer doesn't need to be any more than 3 significant digits, the number used with the fewest significant digits, because it doesn't mean a lot. Your answer cannot be any more accurate than your input. Okay? It's like measuring something. If you have one measured to the millionth place accuracy, and you build something and then something else is measured to the 10th place accuracy, listen, you don't need that millionth place business. The 10th place is going to have to be enough, because the 10th place one is not as accurate as the millionth place. Did that just sound like a big circle to you, or does that make sense? You can't be any more accurate than the least amount of significant digits. I didn't see any of that in homework, by the way. All right, round off errors. Okay, non-zero digits are always significant. So remember we counted them in the last slide, so keep this in mind. Non-zero digits are always significant. Zeros before other digits, if you're talking about in whole numbers, are not significant. So let me go back to my picture. Notice we counted significant digits here. If I would put, I'm trying to pick a good color, if I would put numbers before there, these dudes right here are not significant digits. We counted them 1, 2, 3, 4, 5, 6, 7, 8 significant digits. So numbers to the left of a whole number are not significant digits. Let's keep going. Okay. Zeros between other non-zero digits are significant digits. So for instance, if I had, instead on the other side over here, if I had one, come on pen, if I had 1.023, which is really 1 23 thousandths, don't get me, okay, then that zero is significant, and this would be now 4 significant digits. Okay, so that's 1, 2, 3, 4. So again, numbers on the left of whole numbers are not significant digits. Numbers in between numbers are always significant digits. Let's keep going. Zeros to the right of a decimal point are significant. Okay, so anything on the right of a decimal point is significant. And to avoid uncertainty, zeros at the end of a number are significant only if to the right of a decimal point. So even if, and this might make you think kind of hard, but even if I gave you the number, okay, how about this? 0, 0, 1, 0, 2, 0, 0, 3, 0, 1, 0, 0, 0. Okay? What's significant and what's not? Those are not. This one is, because it's a place, it's holding a place, right? This is significant. You would think these wouldn't be, but you know what? They are, because they're telling you this measurement goes out to the tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 million, 100 millions place. Even though it has the same value as that, right? They have the same value. But this number here tells me that that value is only accurate to the tenths, hundredths, thousandths, 10 thousandths, 100 thousandths place, where this one's accurate to the 1 millionth place. And that's probably more than you ever wanted to know, but that's really important. And if you're building explosives, that matters a lot, right? So if you're going to be a physicist or you're going to teach a physicist, these things matter. All right. That's my last page. I hope you have a wonderful day. Come back for section 7-3 soon, and we'll talk more about decimals.